Hey, welcome to this series. Today is day one, beginning lectures on basic mathematics, or really intro to proofs. I call this the introduction to math as an art form, math as a creative, beautiful subject, worthy in itself, pure math, even. And when I heard that Serge Lang had a book on high school mathematics, this is all of high school math fit into one book, starting from the very beginning, from the integers all the way up through pre-calculus. I got really excited about that. I think that the American education system could be better. Forgive, forgive my cat for photobombing all the time. Luna. So today we will be talking about the integers and rules for addition. So I always like to show an example of one of the types of exercises that you can prove or that you can work after you understand these concepts. So this is the first exercise in this book. And I love it because this is proving a mathematical truth. A truth about numbers. For any numbers, A, B, C, and D, we always have this property. I should say, as an intro to proofs, if you stick with this video to the end, I will show you one of the most beautiful proofs that I know, that I think does not depend on very much beyond literally it just depends on addition, like rules for addition. Okay, so let's read this thing. So justify each step using commutativity and associativity. So if you read the text, you will see the discussion about these terms, commutativity and associativity. I'll explain it quickly. So commutativity is simply this fact that we've all learned and we take for my cat that we've all learned and we take for granted. For any integers, for any numbers, a plus b is the same as b plus a. We could think of this as lengths on a ruler, or if you draw lines in the sand or something. A plus b is the same as first adding b and then adding a. Let's see. Let's do these. Let's do it somewhere else. Combine them together and then line them up. Do they line up to the same amount? Yes, they do. Right? If I look and just line them up, they end up being the exact same length, which is pretty neat. And so this is something that we can believe is true without proof. You can prove this property. This is something that you can prove from simpler assumptions, but right now this is as good of a starting point as anything else, I think. So in this book, we will just assume commutativity of addition is true. Now, if it's your first time working with abstract mathematics or proof-based mathematics, you may be one of the people who say, like, oh, math got difficult for me once letters started getting involved. Try concrete examples. Like anywhere where there's A, B, C, D, try plugging in numbers and seeing what happens. Just get examples for yourself, concrete examples. Is 1 plus 2 the same as 2 plus 1? Yeah. 2 more than 1 is 3, and 1 more than 2 is also 3, right? Nothing too surprising here. So that's commutativity. What is an example of something that's not commutative? Is there anything that is not commutative out there in math? There are. There are a lot of things that are not, in fact. So pause and try to work this yourself. What is something, if you think of the numbers 1 and 2, maybe, a way to combine 1 and 2 where where these two are not equal. I think that you found it. A minus B is not the same as B minus A. If I have one apple and then I try to eat two of them, that doesn't even make any sense. 1 minus 2 is not even a number yet. We will invent it later. That would be -1. It would be -1 in the integers, but it does not exist in the positive numbers, right? Either answer is valid here, but on the right-hand side, there's only one solution. 2 minus 1 is 1. And certainly, -1 is not the same as +1. Does not exist is not the same as +1. So subtraction is an example of something that is not commutative. Subtraction, not subtraction. Cool. It's good to keep examples in mind. Anytime that I define a concept in math, I want to give an example of somewhere where that's not true, then that helps justify the fact that we are talking about it in the first place. Some mathematical facts, though, are more useful to be used to prove other facts. Associativity. This is a pattern that says that A plus B plus C, we can group parentheses in different ways. We can add B plus C to A, or we could add C to A plus B, right? In addition, we don't actually need parentheses, though. If we are only working with addition, we can have A plus B plus C, and you don't need to write parentheses everywhere because of this associative property. But what about something that is not associative? Let's try our good old classic subtraction. What if we try 1 minus 2 minus 3 versus 1 minus 2 minus 3? Okay, so the first line is 1 minus 2 minus 3 is -1. 1 minus -1 is 1 plus 1. This is 2, right? The second line, though, we have 1 minus 2 is -1 minus 3. -1 minus 3 is -4. So subtraction, again, is non-associative. If you think of subtraction as an operation. These two reasons are why it's very valuable to add the concept of negative numbers. Because if we call subtraction the addition of a negative number, the addition in the other direction, then we can add in either direction. Like we have commutativity of addition all the time. We have a commutativity of addition, including with negative numbers. Okay, so rewriting this, 1 minus 2 minus 3, if we rewrote that, this would be 1 minus 2 plus -3. Well, we still aren't, that's not going to change the fact that these two are not equal. But, okay, so now we've defined commutativity and we've defined associativity. Let's use those to prove a couple of cool things, I think. One, if I have 5 apples, if we just work with the whole positive integers, we get one really nice result, I think. 5 is 5. 5 is also 4 plus 1. We could say that it's 1 plus 4, but remember that we're calling commutativity, we're just going to consider 4 plus 1 is the same as 1 plus 4. Let's just treat those two as essentially the same. But it's also the same as 3 plus 2 and 2 plus 3. 3 plus 1 plus 1. We could also share apples. 2 apples to player 1, 2 apples to player 2, 1 apple to player 3. We could also do this. And we could also do this. So these are all of the ways to add positive numbers to equal 5, up to reordering, up to commutativity. If we consider 4 plus 1 is the same as 1 plus 4, here's an example. There are 7 partitions of the number 5. This may not seem like it, but counting the number of partitions of a number, there are still open questions about this. There are still unsolved math claims and beliefs, or things that we think are true, or just more work is still happening. And some really beautiful work was proved and completed about 100 years ago with Ramanujan, a famous mathematician. So we'll be seeing examples about this more as we keep coming back and adding more proof-based math. But just here's one example of all we have is just addition of numbers, and we're not even using any parentheses, because if you're only adding numbers together, associativity says that you don't need to write parentheses. Okay. So this is the 7 partitions of the number 5. Okay, so let's see. First, let's work this exercise. Why don't we do this exercise? I'm going to do it at the very end, so I definitely have enough space. So we're also assuming that these are numbers. It doesn't yet say A, B, C, and D are numbers, but I think that we can assume that. All right, so proof. This proof is of the form left-hand side. We want to show that the left-hand side equals the right-hand side of this identity. One way to do that is to assume the left-hand side, rewrite it until we get to the right-hand side. And this is the method of proof that this exercise is asking for. So let me erase that, and I'm actually going to remind ourselves, we start with the left-hand side, and we want to use commutativity and associativity to prove this identity. So A plus B plus C plus D is equal to, well, we want ultimately to have A plus D on the left and B plus C on the right. So maybe, I noticed that C in the final form, C is all the way on the right. So maybe my first step that I'm going to do is to try to move that C to the right. I literally think that this is like playing a video game or something, like a little puzzle that you're allowed to make certain moves at every step along the way. Like this is it's like one of those puzzles where you have to slide, a block, and then you can slide other ones until you get to the final configuration or something. So this step was, we have to justify every step. This step was by commutativity. Commutativity, we said that C plus D equals D plus C. I'm going to try not to be moving the iPad around like crazy. Luna, you're so cute. You're so cute. Okay, next we have a addition in the middle. We can, this is right now in the form of x plus y plus z, where x is a plus b. We can rewrite that as x plus y plus z. So, by associativity, I know that this is a plus b plus d plus c. This is by associativity. Now this step, again by associativity, this is a plus b plus d plus c. This is a plus d plus b plus c. So we used associativity again here. Then I used commutativity. Then, this is not the beautiful proof, by the way. I just want to be clear about that. I just wanted to work this exercise. I think it's a nice one. It's worth doing this at least a couple times in your life to get used to seeing these. But it gets a little clunky, like when you're really writing these associativity truths or something with the parentheses, but it's worth doing. So in this, I used associativity, right? Now, remember that this is now in the form x plus y plus z, and I can rewrite anything like that as x plus y plus z. This is a plus d plus b plus c. Was that the final form that we wanted? Yes, a plus d plus parentheses b plus c. Now we are done. So at the end of a math proof, every step along the way I've justified my steps. I used shorthand, but by associativity, by commutativity, associativity. At the end of a math proof, it is conventional to draw a cute little square. The cute little square says, therefore, we are done. We are done. Like it's like proclaiming, like, thus the proof is complete. Another way to do this is to write QED, which I believe is Latin, and it means, therefore, it's demonstrated. Okay, there we go. There's one exercise. We've solved your first ever proof if you worked it with me. Thanks for watching that. Now, let's do the really fun thing. In my opinion, this is truly a beautiful proof. Beautiful proof number 1. This is by Gauss. Those who have studied math for fun may have heard his name many times. Uh, Gauss proved many things about prime numbers as well as other fields of math, but one of the most prolific mathematicians ever. There's a famous story, and who knows if it's true or not. I mean, I like to think it's true, but there's a famous story that when he was in elementary school, when he was 10 years old or something, when the class was acting up, when the class was getting rowdy, the teacher made them practice and said, okay, add all of the first 100 numbers. Okay? So let's see. What does that mean? Like the exercise, the assignment was to add, if you just have the first number, it's just 1. 1 plus 2 is 3. 1 plus 2 plus 3 would be 3 plus 3 is 6. 1 plus 2 plus 3 plus 4 is 6 plus 4. 1 plus... Now I'm going to start using dots just to save some space. But notice that 1 dot 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 plus 5 is 1 through 4 plus 5. So I can take the previous 10 plus 5 is 15. Right? So if I could, I'm going to write this as 1 plus dot 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 n, and this is some capital N for the total or something. Okay. This is not the worst way to spend an afternoon, I feel. You could spend a little bit of time practicing this yourself, and you don't have to draw all the numbers every time if you don't want to. What is 1 plus 2? 3. What is 2 plus 3? What is 3 plus 3? 6. What is 6 plus 4? 10. Plus 5. Plus 6. Plus 7. Plus 8. Plus 9. Plus 10. Plus 11. Plus 12. Right? Dude, this is not the worst way to spend 5 minutes. Like, it's better than TikTok, right? Like, how far can you go in this? Can you actually get to all the way up to... Can you do this 100 times and find the 100th number in this list? I don't know. One thing is, like, you can kind of save your game and then reset the next day and resume. What was the difference between these two? We found a plus 10, and then from 55 to 66, that was a plus 11. This one was plus 12. Like, math is all about finding patterns and proving that those patterns are always true. But it's kind of the science of patterns and understanding why patterns work. So plus 13 would be 91. Plus 14, 105. Plus 15, 120. So you can do this for a long time, and you can pretend that you're being a rowdy kid in the 1800s or something. But Gauss was clever, and he was really paying attention during the Commutativity and Associativity lectures. He thought, A plus B is B plus A. This is our first math fact. Also, A plus B plus C is the same thing as A plus B plus C. In other words, we don't need to write parentheses. We can just treat all of these as additions. If you keep combining these two and using these two facts together, this is often called regrouping or simplifying, like a collection of numbers. So the challenge was to find the sum of the first 100 numbers. Gauss said, let's call that n. Whatever it is, there's some number, and that's the answer. Maybe I could use the letter A for answer, but I'm going to add all the numbers, and that equals something. But by commutativity, by using commutativity and associativity again and again, you could also write that backwards. Right? Let's get one more column in this. I should have predicted this. Let's get one more column here. So the second number in this pattern, in the first line, it's 1 plus 2 plus 3 plus 4 plus 5 plus 6, blah, 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 up to 100. In the second line, it's 100, 99, 98, 97. So we're just adding all the same numbers backwards, which maybe is easier to do in some way for some reasons. Gauss noticed, wait a minute, dude, what if I added these two lines together? What if I added these two lines together? So what is 1 plus 100? This is 101. What is 2 plus 99? 101. Every single column adds up to 101. And then on the right-hand side, this is 2 times n, right? Well, how many numbers are there in this list? It would be the same as the original list, and there were 100 numbers in total. 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 100. So there's 100 terms in this. So then that means 100 times 101 equals 2n. If that's true, then n is 100 times 101 divided by 2. 100 divided by 2 is 50 times 101. 50 is 5 times 10, but in any case, this is 50, 50. So, and he was done. And then he went back to, probably studying prime numbers or something else. I don't know if he would, be noisy or something. I think he would probably be studying prime numbers again. But it's incredible. Like, I think that this is a really clever, pretty, beautiful proof. And who knows if it actually was Gauss or who came up with this idea, but this was clever. This was quite clever. And all it relies on is essentially commutativity and associativity. If we wanted to write it a little more carefully, I could do it in one line instead of in 2 columns, but it's not too important. The really cool thing to notice here is that the number 100 was not special. There's nothing really at the end of the day that this proof relied on the fact that it was 100. It could have been anything. It could have been 123 or something. In this, we added 1 plus n. So everywhere, these are all n plus 1s. N plus 1, n plus 1. And instead of 100, there's n of them. So in general, Gauss proved that the sum of the first n integers is n times n plus 1 divided by 2. I honestly do think that this is a very pretty proof. This is a very nice, very beautiful, elegant, clever proof. And yeah, if you want to write it in a textbook, it takes like a little more typesetting or something, but this is the idea and it works. Like, this is a fully rigorous, formal proof that I think somebody can explain to a middle schooler. And very last thing, let's just see that it worked for all the numbers, for some of these numbers that we've picked so far. When n was n times n plus 1 divided by 2. In this first one, n was 1, so 1 times 2 divided by 2 is 1. 2 times 3 divided by 2 is 3. 3 times 4 divided by 2, 12 divided by 2 is 6. That matches this 6 right there. 4 times 5 divided by 2 is 20 divided by 2 is 10. 5 times 6 divided by 2 is 30 divided by 2 is 15. And then in the last one, 6, oops. Oh, I'm glad that we got one of them today. 6, 7 divided by 2 is 42 divided by 2 is 21. And we got it. So what better place to end? Yeah, thank you for watching. So there's our first, in my opinion, beautiful proof. And, share it with all your friends. Like, I think it's a shame that we don't test for this on the SAT. Like I really think that the SAT should ask, prove that 1 plus ... n equals n times n plus 1 divided by 2. And I don't know if it'll be next time, but sometime soon I'll show you another proof of the same exact fact. And it's a little less clever, but it's very beautiful in other ways. And to just wrap up this video on one last thought, if math is an art form, there's something about art, how do I put this? I feel that if you want to call something art, there has to be some element of beauty in the thing. I feel that proof that we just saw is beautiful. I feel that is kind of clever. Oh, that was really cool. Dang. Oh, wow. I converted something that was 100 additions into, 99 additions into a multiplication and a division. Something that was 99 operations and now is just 2. Or n operations is now, 2 operations. That's one argument for this thing. There's another argument that's also very nice. And then there's a concept of, which argument is nicer? Which argument is more beautiful? Which one should we memorize? Which one is better in some sense? And there's a subjective nature to that. There's another very beautiful proof of that same fact. And I want to find out in the comment section whether you all think Gauss's proof is more or less beautiful than the proof by induction, which we'll do sometime soon. So thanks for watching. Please do hit the like and subscribe if you enjoyed this. We are also starting a weekend group lesson course for adults who want to study math as a hobby for fun. So if you're interested in that, shoot me an email at jcpractices@gmail.com. You can find that email in the video description. So thanks so much for watching. I had a blast, and keep an eye out for my practice sessions. I'm streaming daily practice sessions almost every single day, working exercises and hanging out and chatting with people and getting a lot of fun little Luna moments. So thanks for watching. Take care. Bye. Bye.